for number 10, they want us to use algebra, the first derivative, and the second derivative to find the following information. Show all work, including the number lines. So, needless to say, we have a lot to do on this problem. It's basically a complete graph analysis. So let's get started. For the x-intercepts, we need to set the numerator equal to 0. Now, there is no denominator here, or you could put it all over 1. So really it's just the polynomial itself that is what we're going to set equal to 0. So 2x to the fourth minus 12x squared is equal to 0. And then if you factor out a 2x squared, it's going to leave you with x squared minus 6. And then if you solve, x is going to be equal to 0. Here, x squared is going to be equal to 6. So x is going to be equal to plus or minus square root of 6. So my intercepts would be 0, 0, square root of 6, 0, and negative square root of 6, 0. For the y-intercept, we need to set x equal to 0. So instead of writing the original function as f of x, I'm going to take it out of functional notation and write it as y. So y is equal to 2 times 0 to the fourth minus 12 times 0 squared. So if we solve this, we get y is equal to 0, which means my y-intercept is 0, 0, which we kind of already knew because 0, 0 was an x-intercept and the origin counts as both. The vertical asymptote, we need to set the denominator equal to 0. Because we don't have a denominator, or if you want to call the denominator 1, and that's never going to be equal to 0, we do not have any. So there's no vertical asymptote. For the horizontal asymptote, you need to compare the degree of the polynomial with the degree of its denominator. So you compare the degree of the numerator with the degree of the denominator. There's 3 scenarios. So this would be the scenario where there's no horizontal asymptote because the degree of the numerator is greater than the degree of the denominator, because the numerator technically has degree 4, the denominator technically has degree 0 because there is no x. So this would also be none. Next, I want to find the first derivative. So this is definitely something that we've been doing a lot. So f prime is going to be equal to 8x cubed minus 24x. And then I want to set this equal to 0 to find the critical numbers. So find the critical numbers. So 8x cubed minus 24x is equal to 0. And then if you factor out an 8x, that's going to leave you with x squared minus 3. So then if I solve here, I have 8x is equal to 0, so x is equal to 0. And then I have x squared minus 3 is equal to 0. So x squared is equal to 3. And then if you take the square root of both sides, x is equal to plus or minus square root of 3. And I need to make a number line. Let's see if I have enough room here. So I'm going to put my critical numbers on the number line. So negative square root of 3 0 and square root of 3. And I need to find test values. This is where I put on my calculator y1 is equal to the first derivative, and I use the table. But you could just plug in test values directly into the derivative. You don't have to use the table if you don't want to. But if you plug in values, you should get negative numbers when you plug in values here, positive numbers here, negative numbers here, and positive numbers here. So a lot of information is going to come from this number line. Increasing, this is going to be negative square root of 3 to 0, and then from square root of 3 to infinity. For decreasing, it's going to be negative infinity to negative square root of 3, and from 0 to square root of 3. The local max, this is actually going to be at 0. And we know this because that's where it changes from positive to negative. And if you plug 0 into the original function, you'll get 0 back out, which 0, 0 is kind of a popular answer here because that was our x-intercept as well as our y-intercept. So here it is again. Local minimum is going to be negative square root of 3 as well as positive square root of 3 because that's where it changes from negative to positive. And if you plug those back into the original function, you should get negative 18 for both of them. So those would be your local minimums. Next up is the second derivative. So f double prime is going to be equal to 24x squared minus 24. And I want to set it equal to 0 to find the potential inflection points. So find potential inflection points. So if I do 24x squared minus 24 is equal to 0, I can definitely factor out a 24, leaving me with x squared minus 1, and then the x squared minus 1, this is going to be, let's see if I come around here, this will be x plus 1, x minus 1 is equal to 0. So you could also just move the 1 over and take the square root of both sides, but you'll definitely get x is equal to 1 and x is equal to negative 1. So these are my potential inflection points, and I want to put these on the number line. So I have negative 1 and 1, and if you're using the table feature, then y1 you'd want to put in the second derivative, and if you wanted to just plug these in directly into the second derivative, you could. So if you plug in a number less than negative 1, you'd get a positive value. If you plug in a number between negative 1 and 1, you would get a negative value. If you plug in a value that's greater than 1, you would get a positive value. So this is going to tell us a lot of information. This is going to be concave up from negative infinity to negative 1, and union that with, I'm running out of space here, Let's actually erase that. Union that with 1 to infinity. Concave down is going to be -1 to 1. And for the inflection points, there's actually an inflection point both at -1 and at +1, because there's an inflection point wherever it changes from positive to negative, or negative to positive, either one. So at -1, and if you plug in -1, you get -10 if you plug it into the original. And if you plug in 1, then you also get -10. So this is a ton of information here. If you graph this, so we can use this information to graph. If you want to graph it on the calculator to also kind of confirm what we've done here, you'll see that it looks like this. So we have our intercepts. Let me try to mark some of these. Our intercepts are like right here, and here, and here. That's also a maximum. Our minimums are right here and here, and our inflection points are, right here and here. The window that I used for this, I used 10 for the x max, -10 for the x min. I used -20 for the y min, and 20 for the y max. Your graph doesn't need to be perfect, but this will be our graph. All right, we made it.